Halo, right? Okay. All right. Now, let's have a quick review of where we are, where we're going, what we'll be doing on the way. Okay. Now, for those who weren't here to hear it, or haven't heard it on YouTube video yet, wait till the next person comes in. Ah, there's Ed. Okay. In case you were wondering, the planetarium is booked solid all summer long. And there was just no way they could squeeze us in. The only week it's not is the week the guy's out of town. And that's the next week, the 4th of July week. He's, I guess, on vacation or meetings or something that week. So this sort of like his work-study student said, maybe we can run it for you that week because we don't have anything scheduled. And he kind of nixed that idea. I didn't get to talk with him, but he said, I don't think it's really right having students teaching students or whatever, however he's going to phrase that. But the other hand, I said, look, it wouldn't bother us any. And the gal that I was talking with said, well, but the thing is we've got all brand new equipment. And it sort of sounded like the fear was they may mess something up and he would be there to help correct it. So it's off. But you still have an opportunity. Every Thursday night, didn't I say 8 o'clock when I announced this before? I believe that was right. Every Thursday night at 8 o'clock, they have a special deal there at Sanford at the Christenberry Planetarium. Open night, open to the public, and it's usually a pretty good crowd, and they always have a good time. If y'all want to go to that, when you go, I would say take with you something that says this verifies that your name was there at the planetarium and attended the showing, and have the date and stuff on it, and have someone there sign it. So every Thursday night except next week. Yes.
If we do that, is there a certain time we have to stay there?
Say this
Is
one.
there a certain amount of time that we have to stay there?
Is there any length of time you have to stay there?
Yeah, because like when I did like bonus opportunities like at school, they were like, well, you have to stay for an hour, like, you know what I mean?
Yeah. Well, if you're going, it's just not worth it just to go there and get signed and come back. I mean, you're not learning a thing.
I'll stay there.
Yeah. So I mean, stay for the show. It's not that long, and I think it will be very enjoyable. And if you bring me that slip of paper showing that you were there, they may have one there already, but I would take one just in case they don't. Bring it back, and I'll give you credit for the lab that we didn't get to do. It's an optional thing. No one has to do it, but if you do it, you get a 25-point lab that you get to replace some other lab with. Okay? It's an optional thing, a freebie, a bonus that you, because you're going to get to drop at least one lab anyway. If you go to this, you then get to drop 2 labs. Okay? So that's up to you. All right. Now, so that's it about, there's no field trip to planetarium this summer, but you can go on your own. We can't do a field trip on Thursday night because certainly not everybody would be able to go, so that would be, but I'll make it all optional, and you pick the Thursday night. Now, not next Thursday. Don't go July 5th because the guy's out of town. They're not having it next Thursday. But this Thursday and all the rest of the term, they'll have it on every Thursday night. I think you said 6 o'clock or 8 o'clock. I don't remember which. You can check it out. Check out Sanford's website, Christenberry Planetarium. They have it advertised. All right. That's it. I've returned to everyone who was here your test 2. If you hadn't already gotten it, I returned those to you. Still waiting on 1 lab 2. Y'all are still working on lab 3. Test 3, there's 3 people who haven't taken that, so as soon as I get those in, I'll return those to you. Lab 4, the one we did last time, quite a few of you weren't here. I've given several of those out today. If you didn't get one, get it before you leave. Okay. So, we're in chapter 18 now. We'll get going on that in just a couple of minutes. But I don't think we'll finish the chapter in time to do a lab today, because the last 30 minutes of today, you have your test on chapter 17. Okay, so get your formula equation sheets ready for that if you haven't already. So your last 30 minutes of that. So that means the 2 hours before that would be our lab time, and I don't think we'll be through with the chapter in the less than an hour we have left. So basically there's no, we probably will get as far as we can in the chapter. We may actually finish it today, but not in time to do a lab. If we do finish it, we'll go on and start on 19. If we don't finish it, we'll have time on Thursday to finish it and then have the lab. Okay. If we finish it today, then you'll have the test on Thursday as well. But we'll see how we go. Any questions on what we've done up till now? Okay, the test on chapter 17 is the last 30 minutes today. So I'll stop by 3 o'clock. So my watch, the pen fell off yesterday, so I've just got it on my desk, but I don't have it on my arm, so I have to come over and look at it. So remind me, don't let me go past 3 o'clock, because that's when I want you to start your test. Any questions? All right. Last time we started in chapter 18, which is covering plate tectonics. And the first subsection here is the history of the Earth's interior. We talked about that. And then we started on the Earth's internal structure. And we talked about different ways we have of validating or verifying this. No one's ever been to the center of the Earth, whatever those corny movies were. They were fiction, not even science fiction, just fiction. Okay? You can't get to the center of the Earth. Nowhere close. Okay? We have barely scratched the crust of the Earth, much less anything else. Okay? So, how do we know that the structure of the Earth, what we do know about it? One of the primary ways we know is through seismic waves. And we talked about this on the last slide. These are basically the waves that are formed when you have these huge vibrations in the Earth's crust or even below the crust. And these are called earthquakes. And what seismology is the study of earthquakes. Seismic waves are the waves that are produced when you have an earthquake. And we did mention last time, not just earthquakes. It just so happens that a nuclear test makes enough vibration in the Earth crust and surface that you can detect nuclear explosions with seismographs. Well, long before anyone had nuclear weapons or nuclear testing or anything, we had this very nice system of seismographic systems all over the surface of the planet. One of the huge successes in science, branched across every ideology and political structure on the Earth. Every nation in the world participates in two things geologically: seismographs and tsunamis, things to measure the waves. Anyone, the one that is near water. Of course, the landlocked countries don't worry about those. But this is one way. Well, what can we learn from those waves? Well, number one, there are three types of seismic waves. Okay? The first is called the P wave. Now, that P can stand for several things, whatever you want it to stand for. The main thing is for its primary wave. But you can also think of it as a pressure wave. Okay? Now, what do we mean by a pressure wave? All right? I'm up here talking to you, right? We hear people down the hall or next door or somewhere talking. How can we hear them? How can you hear me? Because when I'm talking, if you put your hand in front of your mouth while you're speaking, you can feel a little burst of air, right? those are compression waves, okay? And here's a couple things about these compression waves. Number one, they're longitudinal. What does that mean? That means the wave travels in the same direction as the disturbance. Because when I'm making these pressure, there are pressures and rarefactions. My vocal cords are doing that, and that's what you're hearing, because it hits your eardrum. Those pressure waves hit your eardrum, and your eardrums interpret those. Your brain is an incredible device to be able to interpret that and make you hear what I'm saying, or actually going on down the hall or whatever. Well, a longitudinal wave is a wave in the direction of the compression, okay? That's what we mean by longitudinal, okay? Compressional means you make the compressions and rarefactions, the low pressure in between the compressions. These are the fastest waves, and this is a key here. This gives us information about where the earthquakes are, okay? These are the fastest waves, the longitudinal waves, the pressure waves, the P waves, the primary waves. And here is the other big thing. These P waves, primary compressional waves, move through rocks, whether they're on the surface or on the interior. They also move through liquids because they're a pressure wave. Now, I don't know if y'all pool people, that you go to swimming pools or if you've been in your life, okay? You probably notice that you can hear things pretty distinctly underwater, right? Because the sound waves travel quite nicely through liquids. I don't know if you're old enough that you would have ever watched the old cowboy and Indian movies or the old bandits and train robber movies, you know. But out in the Wild West, how the Indians or how the bad guys or how whoever it was wanted to hear whether the train was coming. Of course, they could wait until they heard it through the air, and that was going to be quite a time. I mean, they're not going to have a lot of time to react to that. But what they do is put their ear down on the track, and you could hear the train coming many more miles away, because the sound waves, the pressure waves, travel through solid, they travel through liquid, and they travel through gases. They travel through all three. And these are the fastest waves. And they actually travel more successfully, you know, with less loss in the solid than they do in the liquid or gases, better in the liquids than they do in the gases, okay? So they move through all the materials. All right. The second wave is called the S wave. Secondary, P primary, but also you can think of the S wave as being a shear wave, okay? And what that means, okay? I can remember as a little kid, and it didn't take much to entertain me, I'll put it that way. I can remember when we were out in the yard and we had the hose there. I remember one of the things I loved doing was grabbing the end of the hose, pulling it above my head and down again as rapidly as I could, and watch that move down the hose. Okay? That was a shear wave. That was like a secondary wave. It's a transverse wave, not longitudinal. Because if you think about it, my action was up and down, right? But the wave went that way. So the wave was perpendicular to the motion. Whereas a compressional wave, the motion is in the same direction as the promulgation of the wave. So this is a transverse wave, a shear wave. Okay? This is second fastest. Okay? That's going to be important later. We're not too worried about that yet. But here is the key. The secondary waves, okay. Can I do a transverse wave through air? Any of you see that? Or feel that? No. A transverse wave will not transmit through a gas, nor will it transfer through a liquid. Only through solids. Only through solids. Okay? Do not travel through liquids. Hang on to that thought. The primary waves travel through solids and liquids. The secondary waves, the S waves, the transverse waves, the shear waves only travel through solids, not through liquids. And then finally, the third type of wave is the up and down, crest and trough wave, think of this as a surface wave. Okay? It's not happening through the earth. It's happening on the surface of the earth. Okay? The best example of this, any of you ever been fishing? Okay? And you have the bobber out there on the surface to tell you when the fish bites, right? Well, a boat comes by and the bobber is going up and down. Okay? That is the up and down, crest and trough surface wave. Okay? If it was under the water, you wouldn't see that motion. Only on the surface you do. So when these earthquakes, when these waves reach the surface and they have nowhere else to go, then they propagate along the surface. Those are your surface waves. Much like water waves, these are the slowest of the three waves, and they occur where the S or the P waves reach the surface, like I just said. The S and P waves come through the Earth's interior, where the earthquakes occur, and when they reach the surface, then they promulgate themselves on the surface as the surface waves. So these are, to me, the least important of the waves. Okay? Now, our seismographs will record these. They will record those, but they really record those because they're on the surface and they pick up these big time. So you'll see if you're watching a seismograph, happens to be at a time there's an earthquake somewhere, you'll see a little P wave followed by a little S wave, and then you'll see surface waves like crazy. But you'll sense these two on the seismograph long or a bit before you'll notice anything here. You'll never feel the others. You feel the surface waves. All right. Now, here are the examples I was talking about. I was giving sound waves as a compressional wave. This, to me, is a little unrealistic, maybe. I can't imagine a spring that will stay that horizontal for very long. But if you had one that would stay by itself horizontal and not sag in the middle, and you pressed on it and pulled back, you see this pressure wave actually makes its way down the spring. Okay? It'll hit the end and then comes back. Okay? And the rarefaction, which is where it stretches back out again, will make its way down and come back. They left off the compression part here, I think. They actually hit the wall there, and then if you have a right system, you'll actually see it come back too. But at least you see it going that way. The motion is in the same direction, the particle motion is in the same direction as the wave propagation. Whereas me and the hose or string tied to a stick or something like this, and you go up and down with it, the particle motion's up and down, the string motion's up and down, the wave propagation is this way. That bump will move down and actually sometimes invert and come back. Okay? Pretty interesting to see. So those are the first two types. Primary pressure compression wave, fastest wave, secondary S wave, shear wave, transverse wave. You've got call them lots of things, second fastest. These go through solids, liquids, and gases. These go through solids only. Okay. Make sense? So what? Okay. So, let's talk about the Earth's internal structure, then we'll come back and see why those waves make a difference, how they make a difference, what we use them for. So 3 main zones. The crust, okay? Now let's get the diagram up here too. The crust is this incredibly thin little skin on the surface of the Earth. Now that's where we live. I would hazard to say none of us have ever been into the mantle. Now, if you're a very, very, very deep miner or researcher and stuff, yeah, you may have gotten into the mantle a little bit. But generally, everything we do is on the surface of the Earth. Okay? That goes down a few miles. Now, that sounds pretty thick to me, especially if you're talking about down deep. But compared to how big the Earth is, that's just the skin. That's just a thin little layer. Okay? That's the crust. Thin, outer thin shell. Focus on the thin. The mantle is much thicker than the crust. And this is the mantle. This is the part in here. Now, there is a part in between what they're showing as the crust and the mantle here. We're going to talk about that in a minute. Okay? It's sort of part of the mantle also, but we'll talk about that in a minute. This is the thick part of the mantle here. Now, what about it? Much, 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 much thicker than the crust. And the crust and the mantle are both totally solid. Okay. Now, we get to the core. Oh, and by the way, if anyone, any research or anything has ever been in the mantle, they've just barely gotten into the mantle. No one's gone very deeply into the mantle at all. So no one has come close, anywhere close to the core. So what's the core? That's the central part. There's actually two parts of it. The outer core and the inner core. Okay? Now we'll get to the description in just a minute. Let's start with the crust. Covers the entire earth. Now you might say, hey, but wait, most of the earth is covered by water. Yes, but underneath the water is solid, okay? Sometimes that's more than a mile deep, but it's still solid. That's the crust, okay? Now, that leads to the two types of crust. There's the continental crust and there's the oceanic crust. The oceanic crust, in general, is much thinner than the continental crust, okay? But it's different in other ways. The type of rock is usually a basaltic rock. Remember in the last chapter, a basalt was a high iron content, very dark in color, that's because of high iron content. That means it's denser. High iron content makes it denser too, makes it darker. Basaltic rock, small, fine crystal size, because generally basaltic rock cools rapidly, mostly because it comes from volcanic action underneath the surface of the water. That magma comes to the surface and cools very quickly because it's underwater, okay? So that's going to be a very, very quick cooling, which means a small particle size rock, basaltic rock. Those who were here for lab, the black tile that we used in our bathroom is almost certainly basalt, okay? Now the continental crust is granite rock, okay? If you remember anything about granite, it's light colored, light density, okay? Low density, less dense than basaltic rock. Light colored because it has very little iron in it. Oh, it'll have some. There's always those specks of black in most of your granite. There's a little bit of iron, but most of it is not, okay? They're also large crystal sizes because they cooled very slowly. So the continental crust is mostly granite, not always, but mostly granite, less dense, lighter colored, but much thicker than the oceanic crust. Oceanic crust, much thinner, typically basaltic rock, small, fine particle size, dense rock because it's mostly has a good iron content. Now, just below the crust, before you get to the mantle, there is what they call, and I don't even know how to pronounce it, Mohorovic, I think, or something like that, discontinuity. The crust is up here, the mantle down there, the layer in between is a boundary, okay? It's discontinuous, okay? It's the materials make an abrupt change there. Right? All right. Let me say just a couple of things just as a review. I did return test 2 to everybody, so if you don't have yours, you can pick it up when we stop, have a break, or go to do the test. We're in chapter 18 now. If you didn't get the last lab, I've got it and I can give it to you. I think you were here, weren't you, last time? Yeah, okay. Huh? Okay, you weren't here Thursday when we did the computer lab? Okay, we'll get it. Also, when we have a break or before test or something like that. We do have the test on chapter 17, the last 30 minutes today. The odds are we're not going to get far enough in 18 to have a lab today, so that'll probably be this coming Thursday. And we'll see how far we get today, whether the test will also be Thursday or not. Okay? And I hope you heard that we're not going to the planetarium. They're booked solid. We had thought they might be able to take us the week of the 4th of July because the guy was out of town, but it sounded like a couple of things, primarily being that he didn't want to risk his work-study students running the very new expensive equipment they just got in that they're not all that familiar with, so no, we're not going to be able to do it. But if you do want to go and get your 25 points for the lab that would have been, it's completely optional. Every Thursday evening, and I can't remember what time he said, 6 or 8. But check it out on the Sanford webpage, Chris and Barry Planetarium at Sanford, and you'll see when the showings are. They have it every Thursday night, except for next Thursday. They have it this Thursday, but not next Thursday because that's the week of the 4th when he's going to be on. Okay, and he's not going to have his students running the show either. Okay, I think that caught you up with everything. Okay, so the MOHA. Oh, by the way, the short name for this is the MOHA. Okay, I'll say it a few times. Mohorovicic discontinuity. From now on, it's going to be the MOHA. Okay, that's the mantle crust boundary, and there your seismic waves increases sharply, and I think they've got this backward. I think it increases, the velocity increases when you go from crust to mantle. Oh yeah, that's right. They said it right. Yeah. But generally, you think of the waves coming from the mantle up, so they decrease sharply when they go from mantle to crust. That's what I was thinking. That's the problem. So that's the MOHA, the Mohorovicic discontinuity. The boundary between the crust and the mantle. It's very different materials, so therefore different characteristics. And one of the things is the seismic waves travel faster through the mantle, more slowly through the crust. Okay? It has to do with density and other things like that. Now here's the picture that sort of illustrates that. Okay? Now this is not to any scale, okay? Or to a consistent scale. The continental crust is lighter in color. They've got that pretty good. Thicker in thickness, okay? They've got that okay. Sort of scales to that. It's different material, okay? Usually granitic, light colored, low density rock. Large crystal size usually, okay? Now one thing they have a little wrong about this, when you do have the continental crust, the oceanic crust, it usually goes below the continental crust. It doesn't crawl up the edge, okay? The reason for that is denser. It tends to go below, not above. So that's a little weird in this picture, but some artists drew it and didn't know. Underneath both of those is the mantle, okay? This line right here, that discontinuity between the mantle material and the crust material, that's the MOHA. The Mohorovicic discontinuity, okay? Then above the oceans are the oceans, okay? Oceanic crust are the oceans. The oceanic crust is usually denser, finer crystal size, darker, usually because of high iron content, which also means it's denser, and they would be subjected under the continental crust, not crawling up the edge, because they're denser. And the scale up here represents the equal size pores for these. The oceanic crust is almost always going to be heavier. All right, any questions on the crust? let's move on down to the mantle where man has never been. Okay? But here's some things we know about it. That is an incredibly thick shell between the crust and the core. So I would hardly call it a shell. Well, it is because it contains the core. Okay? Now get this. It takes up 80% of the volume of the earth. So you have the tiny little crust out here on the edges. 80% of the volume of the earth is in the mantle. Now it counts for 2/3 of the mass. That's about 67% of the mass. That means the core is much denser than the mantle. Okay? The crust, hardly any density at all compared to these two. Okay? Now, the mineral that makes up the most of the mantle is mainly olivine. And I don't know if you remember from last chapter when we had that illustration, olivine was one of the darkest, densest of the iron ferromagnesium silicates. Okay? Remember your two classes of the rocks that make up most of the surface of the earth are, the primary one is silicates. 92% of the crust is made up of silicates. Two types of silicates. Ferromagnesium silicates, the darker ones, the ones that have iron in them, and non-ferromagnesium silicates, the lighter ones, like the granites. Okay? So those are I'm talking minerals and rocks there. Olivine is the mineral that makes up this. Very high iron content, but it's still a silicate, ferromagnesium silicate. Okay. Now hang on to the thoughts about 80% of the volume, 2/3 of the Earth's mass. Okay? Now, how do we know this much about the mantle? 3 data sources. And we talked about some of these in the earlier. The seismological data, now we haven't told you how yet, but that is the number one thing. It tells us lots about it. As you just saw in the previous slide, the sound, the waves travel much faster through the mantle than they do through the crust. Okay? Now this next one, to me, just about blows my mind. How do we know about the mantle? Well, the nature of meteorites. What? Meteorites are those rock fragments that are floating around in the solar system that sometimes hit the Earth atmosphere and burn up on the way down, and those that make it to the surface, those are the meteorites. Okay? How does that tell us what the mantle is? Well, we think they're made out of the same material. Okay? So that is a stretch in my mind, but they do believe there's a lot of continuity or similarities there between makeup of meteorites and makeup of the Earth's mantle. But this to me makes great sense, the materials ejected by volcanoes. Okay? Obviously, the liquid that's coming out either was next to or part of or even come through the mantle. So the materials that come out there are going to be pretty similar to what's in the mantle. Moreover, and we'll talk about this in a couple chapters to a little bit more detail, maybe even next chapter. When you have a volcanic explosion, you have a mixture of things coming out. Of course, you have magma coming out, but once it reaches the surface, it's called lava. That's liquid rock. But that's not all you have. You have solid rock that sometimes when the explosion occurs, that was sealing up the old volcano, and then it blows that out. So you have those solid rock. But you may also have chunks of rock that didn't completely melt inside with the lava. And that's being brought up too. That would be the best source of what is in the mantle, because that's probably where it picked up those rocks are in the mantle. Okay. Now let's get back to the basalts. the basalt correlation. These are close to silicate chemical. This is going back to this one. Those basalts, the material that's brought up in volcanic activity, reaches the surface, solidifies, small crystal size, so it solidifies fairly rapidly. These are close to the silicate composition of the stony meteorites. I mean, that's where it comes from. The stuff that's coming up from the earth and hardening there is very similar to what you see in the stony meteorites. Not the necessarily all the meteorites, but more the stony. And the basalts are the most common volcanic rock. That's how they form the oceanic crust. Volcanic explosions, they form the crust down there. Now, certainly there's crust on the earth, on the surface of the earth. It's also volcanic. Think Hawaii. The entire island chain of Hawaii is there because of volcanic eruptions that have kept coming up and up till they broke the surface and now an island chain. In fact, most islands that are out there in the middle of the ocean, they are volcanic materials. Okay? But even interior in the U.S., okay, it was last summer, I think it was, my wife had professional meetings in Park City, Utah, which is near Salt Lake City. And because I had the week off between terms, we decided to go out a little early and do some touring around and seeing things. And then while she was in her meetings, I was working on stuff in the hotel room, or out sightseeing by myself. But when we were driving through some of the areas in Montana and Idaho, we were in some really incredible rock formations that were called the basalts. What? This was up at really high elevations, and yet they were basalts. Okay? How in the world did basalts get up there? Well, this is Jordan. Okay. Well, because the Earth's surface never changes. I mean, it's always changing. Always changing. And these things that were one time bottom of the ocean have been uplifted. Way uplifted, but it took billions of years for that to happen, but now they're up high elevations, okay? So not always are these volcanic rock underground, underwater, or even islands. They can be found lots of places. And certainly Kilauea volcano is making lots of new volcanic rock right now. That's the most active it's been for decades now, the most active volcano on the planet, but now it's doing some pretty major eruptions. Before now, it's always seeping out. It's always reacting, and seeping out lava and magma onto the surface, but now it's really doing some pretty major explosions. Okay, they hope it's going to die down within a month or so because it's destroyed an awful lot of houses. And this is just a little side note. It's what my connection with the Kilauea volcano is. I've never seen it. I've been on Hawaii, but always on Oahu, never the big island of Hawaii. The U.S. Navy, I guess, has a little bit of a sense of humor. Not necessarily a lot, but a little bit. This is Christy, right? Okay, we're getting a good crowd today. We're only missing Guy and Lauren. Well, Lauren sometimes comes in a little bit later. Okay. But the Navy, our Navy is better at this than any Navy in the world, and it's called underway replenishment. Okay? They call them UNREPs. Everything is abbreviated in the Navy. Underway replenishment. That means if the battleships are out there, and by that I mean aircraft carriers, destroyers, cruisers, if those things are out there fighting the battles, we have supply ships that keep them supplied so they don't have to turn around and come back into port. So we supply them with food and other materials. Those are the AFS ships. We provide them with oil, fuel. Those are the oilers. We provide them with, I guess that covers most of it. We provide them with additional ammunition, because if they're out there fighting the battle, they're using up the ammunition. So those are provided by ammunition ships. Those are called AEs, auxiliary explosives, okay? And I was on an AE, and its name was, how do they name AEs? Ammunition ships? They name them after volcanoes, okay? And sometimes some of the older ones are after fire type things. So we have the Kilauea, the Mauna Kea, the I can't think of how they're pronounced it. Haleakala, that's it, Haleakala, Mount Hood, Mount Shasta. You have all these ships named after volcanoes, because if they ever do explode, they make a big hole in the water, okay? But they don't. They're the safest ships in the Navy, probably. All right. Because everybody is very attuned to keeping the ship safe. Okay. It's sort of like riding around on a powder keg. Okay. So there's the mantle. Let's go to the core. Not that anyone has ever been to the core. Okay? Now, remember what percent of the volume was the mantle? Volume of the earth? 80%. The core makes up 15%. That means 80% plus 15%, 95%. That means the crust, even though it goes all over the surface of the earth, only makes up a mere 5% of the volume of the earth. So it's a thin crust. Now, what was the percentage of the mass of the earth made up by the mantle? 2/3. What is it of the core? 1/3. That means less than 1% of the mass of the earth is occupied in the crust. Hey, that's where we live. That's where we think it's so much there. It's a drop in the proverbial bucket. Okay? Less than 1% of the mass is in the crust. 1/3 of it in the core. Now, the core, because it's interior, has all the weight of the crust, of the atmosphere, of the crust, of the waters, of the mantle, and everything is pushing in on the core. That makes it very, very dense. That's why it has 1/3 of the mass but only 15% of the volume. It's really, really dense. And of course, the more you press it together, the more friction it has. And the more friction it has, the hotter it is. Okay? So, here's what we've learned through our seismographic data, our waves, seismic waves. The P waves, seismological data, the P waves are refracted by the core, and it produces what we call a P wave shadow zone. Now, what do we mean by refracted? Well, are y'all familiar with light being refracted? Okay? I see that Jordan has glasses on. What do those glasses do for you? And so does Adam. And Pius. What do they do for you? Oh, and Ed. What do they do for you?
They let me see.
Okay, how? They bend the light, depending on what kind of situation your eyeball has. If your eyeball's a little too long, you tend to be nearsighted. So the glasses change the velocity, basically, so it's not much, but change the wavelength so that the image actually forms on your retina. If your eyeball's a little on the short side, then I think that's when you're farsighted. I may have them backwards. And it changes where the image focuses on your retina. That's what it does for you. If you have an astigmatism, it kind of adjusts those. How does it do that? By differences in what they call the index of refraction. Okay? Same thing happening here. The P waves are refracted by the core differently than they are by the mantle or certainly by the crust. So therefore, the waves are bent more. Okay? Here's the illustration of that. Here are the P waves. Let's say that we had a seismological incident right up here. Okay? In other words, an earthquake. It's into the mantle somewhere there. It could be near the surface, but let's say it's into the mantle somewhere there. It sends out P waves in all directions. Okay? P waves in all directions. Those that happen to go through the core, here they're spreading out through the mantle as you would expect. When they hit the core, they're refracted and bit back inward. Okay? Then when they start leaving the core, they spread back out again. When they hit the mantle again, they spread again. But what they've left is a shadow zone. Okay? If there was not the core in there, these all would come out this way. They would all be uniformly spread. There has to be something in there that made the shadow zone. So they've done the models and stuff like this and found out, hey, it must be something with greater density, blah, 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 and they figured it out. Greater density in here than it has out here because of the way it refracts it. So this is the model and it fits the shadow zone. So before it hit the edge of the core, all these P waves come out here and following regular patterns all around, three-dimensional, okay? But anything past 103 degrees, you don't see any P waves. Up to about 142 degrees. That's 39 degrees shadow zone there. After that, you see P waves again, okay? You know they're from the same earthquake, but nothing in that big 39 degree band around the opposite side of the earth. So from 103 degrees, from wherever the incident occurs, the earthquake occurs, for 103 degrees in all directions, you sense these P waves on the seismographs. Then you have a band that no seismograph in that band from 103 to 142 going to pick up anything. And you know there was an earthquake, but you say, oh, it's too far. No, it's not too far. These on the opposite side of the earth from the earthquake still pick it up. It's that shadow zone. That's only accounted for by a core. Okay? Now, the models that determine that, the size of the core are pretty much determined by this 103 degrees. Okay? You can always tell the boundary of the core. That's the shadow. Okay? Now, modeling what's going on in there, that's what tells you to make the model fit the data. You have to have two different densities in here. One inner, one outer. So that's how we know there's an inner and outer. Okay. So the P waves and all this you get from your, all this information about the core from your seismic waves. No direct P waves seen, blah, blah, I've talked about that. They're used to calculate the size and the shape of the core. That's basically giving you a very general way to do that. The source of data, this source of data on the interior tells us something about the makeup of it. Also, that they come together, denser in the middle and not quite as dense from the outside. Okay? Now, make sense? So it tells us a little something about the makeup of the core as well. Okay. Now this picture isn't, it's probably not too far off from scale. I would say they have it a little too big because that looks like more than 15% of the Earth's volume. So I think they did this to make it easier for us. Okay. But anyway, that's what's happening. That's what they observed. This is the way they can explain it. All right. Now, what about those S waves, though? Wouldn't they follow a similar pattern? They're just a little bit slower. Not that much slower, just a little slower. Okay? But the S waves have a larger shadow zone. Whereas the P waves, only between 103 degrees and 140, whatever, 2 degrees, look at the S wave shadow zone. Absolutely nothing gets through anywhere past 103 degrees. Nothing. Now, if the P waves can get through, why can't the S waves?
Because P wave, when we got pressure,
waves travel through liquid. Gas waves will not travel through liquid. Now notice how they drew the waves. They drew the waves like this. They're transverse waves. The material is going like this while the wave is propagating like this. They have the same limits here, 103 degrees. That's the edge of the core. That's the same. The difference is none of them come through the core. And the only explanation that anyone can come up with is that the core has to be, at least the outer part of the core, has to be liquid. Because shear waves, transverse waves, cannot propagate through liquids. Pressure waves, compression waves, primary waves, they do. Shear waves do not. So therefore, the outer part of the core must be liquid. Okay? So this is what tells us the outer part of the core is liquid. Larger shadow zone, anything beyond 103 degrees from the epicenter. We'll talk about what that means later. The core acts like a liquid, not allowing S-shaped propagation. So if it acts like a liquid, it must be a liquid, okay? Or have liquid features. But the core has two parts. The outer part of the core is liquid. The inner part is solid. That's what accounts for, oops, wrong way. No. The diffraction, the extra diffraction you have inside the core, the P waves. It must have a solid inner core in order to do that. And it makes sense too. All that more pressure and stuff, the heat is what makes the outer core a liquid, but then all the pressure, even that liquid gets pushed together so hard it becomes a solid again. And that makes sense. So the inner part is solid. And it's supported by the combination of the S wave, shear wave, and the P wave, pressure wave data. Okay? Make sense? Now, other core evidence. And here they go back to the iron meteorites, okay? The iron meteorites are mostly iron and iron nickel alloys. Guess what the core is? Mostly iron and iron nickel alloys, okay? It's thought to mimic the chemical composition of the core. Why? Well, where are they from? They're from the remnants when the planets were forming. And so there would be more like the composition of the inner part of the planet. Now another piece of evidence. The Earth acts like a magnet. Right? When you have a compass and trying to figure out where you are, the compass is usually going to point toward the north. Why? Because like poles attract, unlike poles attract each other. That compass, which is magnetic, is going to point toward the opposite pole of the Earth. And the Earth acts like a magnet. Now, why would the Earth act like a magnet? What produces magnetism? Okay, now this was in the first half of the book. You haven't had it, you don't necessarily know it, I'll tell it to you. Moving charges induce magnetic fields. Always. It's the moving charge makes a magnetic field. Well, where are the charges? The source is in the turbulent flow within the liquid core. Okay? In other words, if you didn't have a liquid core, you would not have a magnetic field necessarily. The models are hard to come by that would do that. So here's what's happening. This is gross, general. It's not necessarily specific. It's my idea of what it is. You have the Earth spinning at a given rate, right? Okay. Now that means all the solid particles of the Earth are moving together, right? They got it. You know, they're solid. They keep the shape. They keep the volume. You know, they're moving. Now, the oceans, you know, they move generally with it, but they don't have to follow exactly. I'm pretty sure none of you have been through the Panama Canal, have you? I haven't either. But it takes a while to get through the Panama Canal. Does anyone know why? because the spinning of the earth pushes water up on the east side of the canal and leaves water behind on the west side. So the difference in levels between the Atlantic and Pacific Ocean are pretty significant. So what they have to do is a ship coming in from either direction, they come in and either drop the level or raise the level. And you have to do that several times before you can get to the other side, because the water isn't moving quite with the earth. It has to stay in the same hole, but it doesn't move quite with it. Well, guess what? The liquid inside the earth is not moving at the same rate either, is it? So the earth is spinning around. The solid part is spinning at a constant speed. The inner part, the water, and guess what? That inner part of the mantle is probably not a nice smooth surface. It's probably jagged, different rocks sticking out, so therefore it's going to create some turbulent flow in the liquid core. And that turbulent flow, the knocking off of charges, ions, electrons off one material into another, sets up a movement of charge. That turbulent flow sets up a movement of charge. The material must conduct electricity, so it's more than likely an iron-based material. Yes, it is. Nickel. Yes, it is. Okay, so it must be able to conduct the electricity. So we know something about its composition, and also that it has charges, and that moving charge creates. And by the way, you use the right-hand rule. If a positive charge is moving in a circular path, your thumb is going to point. Your right-hand rule, make your fingers go the way the charge goes, your thumb is going to be where the North Pole is. North Pole. So they know exactly. I mean, it all fits. And the combination of the meteorite data and the magnetic field data is consistent with an iron core liquid on the outside. It makes sense. Hardly any other way we can explain what we observe, except for that. Okay? Any questions? So let's look at a little more detailed structure. Remember when I said there's some other things in there we'll get to later. We're going to look at this a little bit more now. Okay? Before we said the crust, the mantle, outer and inner core. Okay? That's pretty gross. Let's go back to the crust and where it interacts with the mantle. Okay? So here we have the crust. There's the continental crust, thicker, lighter. Oceanic crust, thinner, denser. Okay? And underneath, and right there is what we call the Mohorovicic discontinuity between the crust and the mantle, the upper part of the mantle. We'll go down a little ways in the mantle. In fact, this part of the mantle we call the outer mantle. I'm trying to find it here. Well, I can't see it, but it's called, maybe it's over here. But anyway, the upper mantle, okay, uppermost mantle, okay. And then down here you have the lower part of the mantle, okay. And in between we have another band here. Remember back when I said there was another sort of band there, I said we'll talk about, that was the upper mantle, okay. Or the upper mantle with this part. This part is called the asthenosphere. Okay, it's a shell, that's where it gets its name, sphere, that separates the lower part of the mantle from the upper part of the mantle. Now let's back up a little bit here. When you include the crust and the upper part of the mantle, that's called the lithosphere. Okay, the lithosphere, the solid layer above the asthenosphere that includes upper mantle and crust. Okay. So the asthenosphere is a thin, when they say thin, notice here, it looks almost as thick as the thickest part of the Earth's crust. Now whether they've got this to scale, I don't know. But compared to the radius of the Earth, that's really thin, okay? Thin, hot, elastic. Now what do we mean by elastic? Second? Okay. we usually think of that as being a stretchy thing. Well, really what an elastic thing is something that comes back to its original shape. If you've ever watched a slow motion picture of, and you can pick your sport, a baseball bat hitting a baseball, a golf club hitting a golf ball, a tennis racket hitting a tennis ball, any of those things, if you were to look at a slow motion shot right when they contact, this is hard to believe, but it's true, that baseball almost wraps itself around the bat. Not all the way around, but it does wrap around the bat. The bat also bends a little bit, and then once the hit happens, they both spring back to the original shape. They are elastic, coming back to the original shape. You see, stretching, if it's stretched and didn't come back, it's not very elastic, is it? We want that to come back, right, to the original shape. Okay, that's what elastic is. So this is a elastic, but semi-liquid, not quite all liquid, but semi-liquid. The hot contributes to that layer in the upper mantle. All of the mantle is hot, but not hot enough to be semi-liquid. So for some reason, there's that sphere around there. It's kind of like the outer core, but it's not the outer core. It's that thin part beneath the upper mantle, beneath the lithosphere, and above the lower mantle. Okay? It's distinguished by a sharp decrease in seismic wave velocity. Part of that is because it's semi-liquid. That's going to decrease the speed. Not totally liquid, or else the S waves wouldn't even go through it, but it's semi-liquid. Elastic, it does go through, but you do see that decrease. That accounts for some of that bending, refraction of the waves there. So the lithosphere is the solid layer above the asthenosphere, which includes the upper, it includes all the crust. Continental crust, oceanic crust, all the crust. It includes the MOHO, see, that's they abbreviated it, and it includes the upper part of the mantle. It's made up of rigid plates floating on that asthenosphere, okay? Floating in the upper mantle. This is where we get the concept of plate tectonics, okay? They're not rigid. They move, they grind, they bump into each other, they spread, they come together, they go past each other. That's what seismic activity is. And that's where most of the earthquakes happen. That's where most of the volcanoes get their sources, from somewhere approximately the asthenosphere, that semi-liquid portion. Okay? And that's how we describe what we observed on the Earth, all the earthquakes and that kind of stuff. Volcanoes and other. So, that leads to our theory of plate tectonics. Now, I haven't been keeping up in the book. Let me go back. Sorry, I should have said this earlier. Back when we were talking about oceanic crust and continental crust, the age, the continental crust is up to 3.8 billion years old. Guess what? It's about when the Earth was formed, you know. That's what we're talking about. Whereas the oceanic crust, generally less than 200 million years. That's a huge difference. And part of the reason for that, the oceanic crust is always regenerating, but then also getting destroyed. We'll talk about that later. Density, continental crust, 2.7 grams per cubic centimeter. Oceanic crust, more like 3 grams. Oh, I forgot thickness. Continental crust, from 6 to 47 miles thick. Miles thick. The oceanic crust, which we say is real thin, 3 to 5 miles thick. Okay, guess what, team? That's really thick sounding to me. Driving down 3 miles, 7 miles, 43 miles into the Earth, that's a long way down. That's why I said All of our mining, all of the activity pretty much we've ever done, only in the crust. We hardly ever get to do any sampling or anything in the mantle. Okay, so I forgot that one. The composition is mostly basalt for the oceanic crust, granite, schist, gneiss, and other things like that in the continental crust. Most of the time I don't pay too much attention to the examples. Let's see if 8.1 is anything. That's making a lot of assumptions. Certainly it's worth a read and think what height above which at which the continental crust floats in the mantle. These, to me, I don't see a lot of benefit in that. All right. Before we hit this slide, theory of plate tectonics, on the same page this occurs, 464, there's a closer look, seismic tomography. Does anyone have a clue of what they're talking about there? Tomography. Has anyone ever heard of a CAT scan? Okay, you've heard of it. The T in CAT is tomography or tomographic or something like that. Basically what it's saying is we basically almost use the seismic waves and study their motion and stuff like this to give us a CAT scan of the Earth. Okay, you don't actually go in and look at the things, but you have the waves going in, X-rays, other kind of rays going in and modeling what's happening in your body. That's what a CAT scan. It's non-invasive, but the electromagnetic radiation does penetrate the body and they receive it back. That's what's going on here. So, well worth a read. I would definitely take a look at that. Okay, theory of plate tectonics. This is 18.3. This is the core of this chapter. The chapter is plate tectonics. This is the theory of plate tectonics. Built on 18.1 and 2, but this is it. So here's our theory, and this, remember, is a theory. We don't know this for a fact. It's just that most of the evidence lends itself to support this. Individual continents shift positions on the Earth's surface. What? Continents move? That's exactly what people used to think. They determined, yes, it is. Patterns between the continental shapes can be fit together. Now, someone came up with this idea centuries ago. I don't remember when, several hundred years ago. They just looked at the maps and said, look at here. Looks like South America would fit right into the armpit of Africa, wouldn't it? It looks like the bulge of Africa could fit pretty much into the Gulf of Mexico and the Caribbean, doesn't it? Look at how the east coast of the U.S. slants from east to west, from west to east as you go up. Look how Europe slants the same way as you go up. Look how it almost looks like either Greenland could fit in the Hudson Bay, or maybe if not, Scandinavia could fit in the Hudson Bay. I mean, there's just so many weird looking patterns here, okay? Well, someone first said that. Are you crazy? How can these continents move? They're fixed. They're solid. They're rock. They don't move. Well, we used to think that. People laughed the guy who proposed this right out of science. I mean, I think he probably couldn't get a job anywhere else after he said this. No way. But now we think, wait, okay? The individual continents do shift positions, albeit very, very incredibly slowly. But when you think that we've been around 3.8 billion years, you can move very slowly and still cover a lot of ground in 3.8 billion years. So the pattern suggests this. In fact, the thought now is that we're all once part of a single large landmass called Pangea. Okay? Now when you see the prefix pan, that means overall, encompassing everything. You ever heard someone talk about an epidemic? That means the disease is spread all over the place. If it really goes all over the world, they call it a pandemic. Okay? You'll hear these words. My wife's an epidemiologist, so she talks about pandemic flu or pandemic virus. If we had that, we may be in serious trouble. Okay? The original concept was that the continents have drifted apart, and in fact, that's really pretty close to what's been happening. But that was what they used to call it, continental drift. Now we call it plate tectonics. The plates are moving. Okay? Now, again, let's look at some evidence. Evidence from the Earth's magnetic field. Okay? Now, there's some things here that I cannot begin to describe or explain for you. They're incredible when I think about them, but it's here. Okay. Igneous rock, what does that mean? Igneous. Last chapter of the test today. Igneous means you almost see ignite in there. Hot. Igneous rock were at one time melted. So igneous rock, as they cool, they record the Earth's magnetic field strength and direction. Okay? Because a lot of these igneous rock are iron-based. Remember, our core is mostly iron. Or nickel. Okay? Have we touched that? Yeah, we did, didn't we? Talked about the only two magnetic materials, three magnetic materials, iron, nickel, and cobalt. It says the core is mostly iron and nickel. Real good record there. Okay? Now, when this lava comes up, magma comes through the Earth, mostly iron, comes through, gets deposited. Some of it forms the mineral we call hematite. And several of you did that in your lab. Was hematite one of your minerals you looked at? Okay, hematite is an iron ore. Okay? Can't remember if it's ferromagnesium silicate or not, but it's an iron ore. Okay? Hematite. Exactly the same chemical composition, sometimes is magnetic. And that forms what we call magnetite. The only difference in hematite and magnetite, this is not already magnetized, this is. Okay? The magnetite poles are locked into alignment with the Earth's field when they crystallize. Okay. Here's what we mean. This high iron content comes out of the asthenosphere, wherever it's coming from. Okay? Makes its way to the surface. It's molten, it's liquid, it settles out and solidifies. Okay. Now, if it's iron-based material, okay, let me back off a minute. Have you ever taken a needle or a pen and stroked it along a magnet? You can make it into a magnet. That's how you make a magnet. Take an iron, nickel-based material that is not magnetized, stroke it along a magnet, you can make a magnet out of it. And you can let it float and it'll point just like a compass. Okay? You know, put it in a piece of styrofoam or something. Okay? You can do that. People have done that. Okay? Now, if you can make that happen when the iron ore is coming up from the center of the Earth and cooling off, the Earth's magnetic field has field lines, right? And if this cools off aligned with the Earth's magnetic field, you can tell which way it was pointing. Okay? And they have done that. They have noticed that the magnetite lock into alignment with the Earth's field when they crystallize. Now, here is the really strange thing. The Earth's magnetic field has varied in strength. Well, that's not too surprising. But here's the part that really gets my goat. It's changed in direction over time. Now, wait a minute. if all our theory of the Earth spinning and the liquid core, the turbulent flow, it would seem like as long as the Earth spinning in the same direction, the magnetic field lines would be in the same direction. But guess what? They aren't. Okay? Now, this is probably not accurate, precise, but it's my little theory of what's going on. Okay? My theory is this turbulent flow down there doesn't always flow in the same direction. It follows some sort of a pattern, slowly changing over time. Slowly changing over time. That would account for variation in field strength. Sometimes they're lined up, sometimes they're not as well lined up. And if it has changed very slowly over time, it may actually reverse sometimes. Very slowly, come back, getting weaker again, then stronger again. Weaker again, then stronger again. Kind of like a sine wave. And guess what? Most electromagnetic radiation follows the pattern of a sine wave. Strong in one direction, very weak. Stronger in the opposite direction, very weak. Stronger in that one direction again, varying over time. That accounts for variation in strength and direction. Now, here is the incredible part. They have actually gone down, taken cores, and have found that at least 22 reversals of our polarity. Pointing that way, that way, that way, that way. Separated by the times when there wasn't much magnetic activity at all. That's when they're on the weak side. Okay? Now this has taken 4.5 million years of, when they study these things and estimate the time and stuff like that. 22 reversals in the past 4.5 million years. All right, pretty interesting. Wow. So what? What does that have to do with plate tectonics? Well, here's what it has to do. Coming up soon. The station near you. Okay. Here's what they mean. As long as the Earth's magnetic field is in one direction, the cooling lava lines up, the magnetite crystals preserve the orientation of the Earth's magnetic field. That's what happens every time the magma cools, the lava cools. Okay? Well, here we have layer here, maybe a weaker layer here, even weaker layer here. Then suddenly it's pointing in the opposite direction. How did that happen? I don't know. That's my theory, but I don't know. And it's like that for a while, and then it's back this way. And if you kept going down the cores, you found 22 of these reversals. There's 1, 2 reversals here, 22 of them. Okay, over time, 4.5 million years, they've recorded 22 times when the field has changed. Okay, again, interesting, amazing. I don't understand why, but pretty incredible. Okay, what does that have to do with plate tectonics? Well, here's what it has to do with it. Okay, we're going to the ocean now. We probably know more about outer space than we know about our oceans. Okay, now it's hard to believe, but it's probably true. We can't go down very deep in our oceans, and when you get down there, it's incredibly dark, it's incredibly cold, it's huge amounts of pressure. It's really hard to study much down there. Okay, but they use things like sonar and things like this. They are now studied the floor of the ocean, even though they don't know everything that's there. They know what it looks like now, what its topography is, or at least portions of it. And they found these ridges in the middle of the ocean, places where there's ridges out there. Why would there be ridges in the middle of the ocean? Okay. Now, a lot of these coincide with submarine, meaning below the surface of the water, earthquakes. Okay? Now, there's a rift along the crest. Okay? I thought rifts amount of heat escapes from that crest. Rift means a little breakage there. A lot of heat is coming out of there. Now, one of the earlier versions of this book, editions of the book, came with a package of several CDs. I mean, 4, 5, 6 of these. And some of them had some of the most incredible video I've ever seen. They were taken along the floor of the Atlantic Ocean, way out in the middle of the ocean, and you saw lava just bubbling up underwater. Of course, it's cooling quite rapidly because the water is very, very cold down there. And you just see this all along the line. That's what it is. Large amount of heat escaping from that crest. And this especially happens on the Mid-Atlantic Ridge. Now, where is the Mid-Atlantic Ridge? As you get from the name, the middle of the Atlantic, and there's a ridge there. And why in the world would there be a ridge? Okay? And notice this. It is just about equidistant between South America and Africa, about equidistant from North America and Europe, about equidistant all the way up. Now you run into a little island up here, Iceland. Happens to be smack dab on that Mid-Atlantic Ridge, and it's formed because there the ridges come to the surface. And Iceland is a volcanic island. Volcanic activity almost constantly. It's not like Kilauea volcano, not quite that much, but there. And it's way up north too. You know, it's not. It's north of much of Scandinavia. It's north of portions of Greenland. North of much of the islands in the Hudson Bay there. It's way up there. Okay? So you would think the people that live there, probably the number one cost that they would have annually would be heating their homes, right? In order to live up there, you got to stay warm, right? So you would think they're going to spend a lot of money heating their homes. No, they don't. Because they're on a volcanic island, and they're pretty sharp people. What they do is pump water down onto the hot rock that is real near the volcano, and pump it back up under the streets, into people's homes, under the floors. They stay warm all year long, and they don't pay a dime for it, or maybe it costs a bucket of water. That's geothermal heat. Good source of heat. Now, the couple times they have made some mistakes, they drill down into the rock so they can get the water a little bit hotter and a little bit closer. And drilling down in the rock, they've almost caused a new volcano to erupt. And then they seal that baby back up really quickly. Say, we'll settle the water. But anyway, this is the Mid-Atlantic Ridge. The reason it's a ridge is because the plates there are separated, and they're weak there, okay? And there's lava bubbling up from below there, and that's what's made the ridge. Because you have, and Iceland actually bubbled all the way to the surface, you know. There was really a weakness there, and it went all the way to the surface, but that's what you got. Coming in this way, you see the ridge. Coming in this way, you see the ridge. And in the middle, you see the thermal coming out of that ridge, even though it's really, really deep, really, really cold, they can detect the heat coming from that. So guess what, team? That's where plates are spreading apart. Okay. Now, how does this tie with the electric fields changing? We'll get to that in a few minutes, okay? These all tie together later. Now, not only that, we have oceanic trenches. These are ridges, you have trenches. Now, most of the trenches I'm aware of are on the west coast, South America, and North America. There are other places too, and you'll see those in a later lab, and you'll study those and stuff, but the trenches I know most about are there. And the reason is, if the surface is spreading at the ridges, somewhere it's got to be disappearing, because the Earth isn't getting any bigger, okay? So what's happening These are long, narrow, deep troughs with really steep sides. They always run parallel to the continental edges, and that's where the oceanic crust is subducting, going underneath the continental crust. Because they're denser, they go in the sea, they're lower anyway, and the continental crust, they go up. That's why that picture earlier that showed the oceanic crust crawling up the side, that doesn't, it happens the other way. Okay? So you have these oceanic trenches as well. Ridges in the middle of the Atlantic, trenches along the edges of the Pacific. Okay? Two things going on. Now, here's what we think is happening. Hot molten rock moves up from the Earth's interior, emerging along the rift. Okay, that's where it comes out, that weakness. Okay? Outflows in both directions, creating new rocks. Right? Okay? Now, what is the drilling evidence shown? The thin sedimentary layers near the ridge becomes thicker toward the continent, which means more and more and more layers came there, which meant at one time they were together and they have drifted further and further apart, meaning the newest material is near the current ridge and the older materials are deeper and deeper toward the continents. You find older fossils near the continents, no old fossils near the ridges. Becoming younger, the closer you get to the rifts, because the rifts haven't been there as long. Okay? Now this is, I guess, a decent picture here. The center of the ridge would be right here, the Mid-Atlantic Ridge. That's only by the fossils, the rocks, and everything else. You don't find anything in there more than 0 to 5 million years. Now this is a long time, but the next outer, the green on either side, I'm sorry, the green is that. The red on either side, these are between 5 and 23 million years old. Oh, and then the sort of the, I don't know what you call that, sage green out here on the outer side, those are 23 to 38 million years. And then the blue outside of those are 38 to 53 million years. Then the sort of the pale orange there, 53 to 65 million years. And then this outer part here, that's 65 to 135 million years old fossils and stuff you do not find in the middle. Okay? So, newer rock, newer fossil, newer everything near the ridges, getting older and older and older the closer you get to the continents. Okay? There's that. Okay? Now we get back to our magnetic, because these different layers, 22 reversals over the last 4.5 million years, the paleomagnetic patterns that you see of magnetic strips in the ocean floor basaltic rocks that you get, they're identical magnetic reversal patterns on both sides of the ridge. What you see on this side, you see exactly the same thing on this side. Fewer changes near the ridge, more and more changes the further out. And they're identical patterns, which means the ridge, they one time were together, they've gotten further and further apart in the spread. Patterns match those found elsewhere, providing age determination, how, when this occurred, about how long, that kind of stuff. It's all there. It all fits together. So the theory of plate tectonics fits the data better than any other theory. Okay. Now, this is supposed to be showing sort of the same thing. I just wish they had drawn it more horizontal layers than vertical. This makes it look like everything's vertical here. Really what's happening, and what happened a long time ago, is split, and the stuff coming out of the middle went like this, okay, horizontally, okay, and then more came out here, and then more like that, and more like this. And to me, these would be better served if they were horizontal. They're trying to emphasize the vertical split, but I think they overdid it. Okay, and this is Guy, right? So, all right. Barely made it in the class time. Okay, so now we're only missing Lauren. Okay, this is sometimes about the time she comes in too. A few times she's made it only to the loud part. Okay, so here more examples of it sort of drives me nuts because this makes it look like there are layers this way, the layers are this way, and then you find the magnetic strips, more and more and more of them out here, deeper and deeper and deeper, fewer and fewer here, because this is new recent stuff. So I wish they'd have shown this a little more horizontal and not so much vertical. Okay. Now, by the way, please read the book. I'm just hitting really high points with this slideshow. So now we're on page 467, lithosphere, plates, and boundaries. And by the way, I'll repeat this one more time. If Lauren comes in, I'll repeat it again. We're in chapter 18 now, well into 18 now. Don't think we're going to finish today, but there's a chance we might. The last 30 minutes today is a test on chapter 17, okay? And so that starts in about, what is it, almost 2 now. That starts at 3, right? Yeah, it's when we do. So we have just about an hour. So we might actually finish this before then. We aren't going to have time for a lab today, but the lab for this chapter will definitely be Thursday. Let me back off a little bit more. There will be no trip to the planetarium. Did you hear that? Okay. You can go to the planetarium on your own Thursday evenings. I can't remember if it starts at 6 or 8, but you can check on the Sanford webpage and find out all the information you need. Probably maps, how to get there, everything. Really a great show every Thursday evening, except for next Thursday. The 4th of July week, they're not having it, okay? This week they are, and then. So if you go to it and bring me back evidence you were there, as in a signed thing, you can either make it up yourself or you can, they may have them there. I would make up one just in case they don't have them. Bring back that you did attend the showing. I'll give you 25 points like I would if we had made the trip. And that'll be a lab, optional lab, that will enable you to drop an extra lab if you need to. Okay, so go if you can. It's worth the trip, worth the effort. But since we can't plan it and do it ourselves, I'll let you do it. And you got how many Thursday nights between now and the end of the term? At least 5 or 6, 4 or 5, something like that. Okay. All right, so lithosphere, plates, and boundaries. Remember, these plates live in the lithosphere. What makes up the lithosphere? 2 major components. The crust and the upper part of the mantle. Everything above the what is lithosphere. It's another sphere, by the way. Okay, the core is way deep. Okay, the mantle is above that. There's the lower part of the mantle, then the upper part of the mantle. The upper part of the mantle and the crust, that's the lithosphere. There is a sphere around the lower part of the mantle, underneath, between that and the upper part of the mantle. Anyone remember what that sphere was called? Sounds like a Greek goddess that the capital of Greece was named after. Oh boy, I can't give any more hints that I can think of.
Was it
Okay? The name of the sphere on which the lithosphere sits. Lithosphere is a sphere. Huh? Starts with A. Asthenosphere, the asthenosphere. Everything above the asthenosphere is a lithosphere. Okay? That asthenosphere is a hot, semi-liquid, elastic layer, probably the source of most of the volcanic magma. They didn't say that in the book directly, but the implications of that. Pockets could be anywhere, but that seems to be where it could be coming from. Okay? So the lithosphere plate and boundary, these are the bases of plate tectonics theory, that the plates, the continental plates, float around on that semi-liquid asthenosphere. Okay? The lithosphere is broken into fairly rigid plates. The plates move, there it is, on the asthenosphere, right here in front of you, the asthenosphere. Your earthquakes, your volcanoes, and most of the other rapid changes in the Earth's crust occur most often at those plate edges. Okay? It's where the plates are spreading, you have volcanic activity. Where they're colliding, you have earthquakes and volcanic activities. Where they're drifting past each other, earthquakes and some volcanic activity. They happen most often at the plate edges. Sometimes you have weaknesses in the middle of a plate. Okay? Hawaiian Islands are right in the middle of the specific plate, but they're erupting because there's a weakness, a fault there in the plate. Now, the three plate motions, I just gave them to you. These plates diverge, they converge, and they transform. Diverging meaning moving apart, converging meaning moving together, transforming sliding past each other. Except it's not a very nice, even slide. It's a very irregular slide. Not even much of a slide. That's the transform. Okay. Here's that picture of the plates. And I don't know where best to begin. We live on the North American plate, obviously. And that pretty much is from the western edge of North America, but not to the eastern edge of North America. It goes halfway across the Atlantic Ocean to the mid-Atlantic ridge that goes down here that we saw earlier. Okay? Same thing with the South American plate, from the western edge of South America to the middle of the Atlantic. That's the South American plate. Okay? Let's continue to our west, and you have a large plate here, Pacific plate. Now, a lot of activity goes on there. And part of it is because of that mid-Atlantic ridge. That ridge is spreading apart slowly, very slowly. The Earth's not getting any bigger, so you have a lot of activity on the edge of the Pacific plate. Okay? Some of that activity is converging, and some of it is transforming. Okay? This is your diverging here. Okay? There is a tiny little plate called the Juan de Fuca plate. As far as I can tell, it's the smallest plate they've got here. It does some weird little things up here. It sort of transforms, it sort of collides or something. Tiny little plate. Along the edge of the North American plate and the Pacific plate is the San Andreas Fault. We'll talk about this in a later chapter 2. What's that famous for? Lots of earthquakes. The San Francisco plate of the 1900s or so, the San Francisco plate, that earthquake that happened when the World Series was going on between San Francisco and Oakland, right across the bridge from each other. The Los Angeles plate that happened just a few years after that San Francisco plate. There's always seismic activity along the San Andreas Fault. Okay? Little or big, it's always happening. Then they have the Caribbean plate that goes from the Pacific all the way across here. A lot of Central America is in that. There's the Nazca plate down here, which is colliding with the South American plate and has a boundary here with the Pacific plate. Over here you see a little bit of the way south, part of southernmost Europe here, India particularly, is on the Indian Australian plate. That goes through much of the Indian Ocean out into the Pacific. New Zealand forms sort of a boundary here. Parts of Indonesia form part of the boundary there. And parts of Indonesia and Malaysia and stuff are on the Eurasian plate, other parts are here. And here we have Lauren, just coming in, just barely into the class period. Actually, we're into break period is what we're into. Do you want to take a break now or wait a little bit until right before the test, which is still an hour away, so it's up to you. I can keep talking forever, it seems like. Y'all need to take a break or not? Yay or nay? Lauren doesn't, she just got here. Okay. Okay. What you think? I hear nothing, so we'll keep going. So these are basically our plates. I haven't hit them all. The African plate down here. They don't label it here. But this is, oh, there it is, the Arabian plate. Most of Saudi Arabia with Yemen and UAE, United Arab Emirates, Bahrain. Can't think of all the names of them. Oman. All those are on that plate. The Persian Gulf is the boundary of that. The Dead Sea is the boundary on this side, or sorry, the Red Sea boundary on this side. African plate here. And African plate goes almost to the, not quite the middle of the Indian Ocean, but goes into the Indian Ocean, around here to the Antarctic plate, around here. Now, I don't know what this green plate is here. They don't label it. I didn't know there was a separate one, but they do put a separate plate down here. Filipino plate, I didn't mention that one. Filipino islands are obviously in there. And a lot of the boundaries, you'll find island. For instance, the Aleutian Islands go right along this boundary. Japan itself is boundary islands here. As I mentioned, Malaysia and Indonesia, those islands go here. New Zealand islands are here. Can't think what this is called, in Caledonia or something like that. These band streams of islands are there. Now you have other island chains right out in the middle of the plate. Like I said, Hawaiian islands, and stuff is almost inexplicable why they're there. But you just have other fault lines within a plate. They're not always at the boundary. So, let's go into the three different plate motions. The first being divergent boundaries. Okay? They occur between two plates that are moving away from each other. The prime example of this is the Mid-Atlantic Ridge, moving away. Okay? Occur between the two plates. Molten material from the mantle rises to fill the fissures between the, as they're opening up. So therefore, you're having new crust forming there all the time. Many of it right near that, less than 5 million years old. That's new, geologically, okay? That's new. Often accompanied with volcanic activity, think Iceland. Now, I don't know if y'all remember this. Y'all are so young, you probably don't. But it seems like it was 5 to 10 years ago, Iceland had such a fairly major eruption of one of its volcanoes. It spewed enough ash and stuff into the atmosphere. Let's go back to the figure that showed Iceland. Okay, into the atmosphere, enough dust, debris, and stuff that much of northern Europe had to shut down air traffic because the planes, suck in air to burn the fuel. They were going to be sucking in volcanic ash, which doesn't do a great job on jet engines. So they actually closed airports in Ireland, Scotland, England, I think parts of it were closed for close to a week. Couldn't fly anywhere in that part of the world because of the volcanic activity in one island of Iceland. Okay, so we don't control. We're not in control. I'll put it that way. Okay. So, molten material rises often occur accompanied by volcanic activity, and that mid-Atlantic ridge is the classic example of divergent boundaries. There are other ridges in other oceans, okay? Some of these you can't tell looking at them whether they're divergent, convergent, or transform, but there are ridges there. Some of them have to be divergent, or they all can't be convergent or transform. So a lot of them are, but not all of them are. So those are the ridges, okay? Now here's the picture of it. As you see, down here is the lower part of the mantle. Here's the asthenosphere, and this is what indicates you have the magma, okay, that lives and comes from here. Here, this is oceanic crust here. This is under the ocean. The ocean is just this little bit up here. You think of it as really major, it really isn't. The oceanic crust is deeper, thicker than the ocean generally, but because it's spreading apart, here's sea level up here, so here's the ocean. You have new basaltic rock being formed on either side, and the layers, and they sort of keep pushing out, so it's thicker and thicker here, more and more changes in magnetic reversals and things like that, more and more fossils, older and older fossils up here, very recent stuff in here, because it's just being deposited, okay? And here would be the place where the asthenosphere would probably come closest to the surface of the Earth. So the mantle is not quite as thick, the upper part of the mantle here. This is the crust, this is the mantle, this is the asthenosphere, and then more mantle down here, just to get an idea of that, okay? We'll talk a little bit later of the theories of why this is happening. No one knows for sure. They're just ideas. Now, what I was going to point out, at least in the figure here, this looks like it's magma, mostly liquid here. But you know, they made this look like it's got chunks in it too, which I wouldn't be surprised to find. And what's coming out is not just liquid, but chunks of older material that never melted completely. So this is where they get the likelihood of similarities between, say, meteorites and stuff, because those chunks can reveal a lot about the formation. Okay. So those were our divergent boundaries. Let's move to the convergent boundaries. Okay. These occur where two plates are moving toward each other. Uh-oh, spaghetti-o. What happens when plates are moving toward each other? They're colliding. Something's got to give, okay? Somewhere old crust has to be destroyed. Because they're coming together, what's going to happen to the crust? Some of it gets destroyed. That usually happens in what they call subduction zones. And this is where the old plate goes beneath either newer plate or different plate. This is a belt where one crust subducts under the other. And we got three types of those subductions, okay? The subducted material partially melts, goes back into the mantle. So what was crust goes back into mantle. And the diverging plates, what was mantle, becomes new crust. So you see it's always cycling, always changing. Slowly, really, really slowly, but it's been going on for billions of years. So lots of changes. So here are the three possibilities with these converging boundaries. Let's say we have a continental crust and an oceanic plate. Continental plate, oceanic plate. What you reckon is going to happen? Continental plates are thicker, lighter. The oceanic plates thinner, denser. So what you reckon is going to happen? The oceanic plate goes underneath the continental plate. That's what it means by subducting. And when it does, it's not an easy traversing. Those are ragged, jagged, rough, and they don't really fit too well. So when you have them hanging up and then suddenly letting go, what happens? Earthquake. What happens? Volcano. You crack one of the crusts, and here comes magma coming out. That friction creates a lot of heat. As it says here, the subducting material partially melts, joins the mantle, goes back into being mantle. It was crust, it's now mantle. Okay? So this is going on. The converging continental and oceanic plates, usually the oceanic subducts under it. Now, it's not the best, but it will show a little bit. As I said before, this subduction, that trough we talked about before, along the west coast of the U.S. and South America, North and South America. I can remember I was on a ship out of San Francisco Bay Area, so wherever we went to sea, we went under the Golden Gate Bridge and then out, and we'd be doing soundings, and stuff, and you go just a little ways out, and the bottom falls off. Deep trench, and then it starts coming up some. That's that trench. That was the subduction zone. The oceanic trench crust is being subducted under the continental crust. What's happening along there? If you can feel the globe here, because it has a little roughness to it, there's a mountain range all up and down there. The Sierra Nevadas, the Cascades, can't read it. Oh no, that just says something else. A little further inland are the Rockies, okay? Those are happening. South America, even more pronounced. These are the Andes going there. Why are they there? Because the oceanic crust is going underneath the continental crust, pushing it up, doing that volcanic activity along there. What is the name for basically the whole circle around the Pacific Ocean? Johnny Cash sang a song with this as a title. But I don't think he was talking about this. I fell into ring of fire. Because this is where so much of the volcanic activity is. We've had probably one of the biggest earthquakes ever recorded in Alaska, in the ring of fire. The whole Aleutian Island chain, volcanic. This peninsula here, I bet you that's volcanic. All of the Japanese island, volcanic. Philippines, volcanic. One of the major volcanoes ever has hit the planet, and we'll see a blurb about it. In the Philippines, it's in a chapter or so away. Indonesia, volcanic, okay? I bet you New Zealand is mostly volcanic islands. All up and down the Andes in South America. Major earthquake in Chile, just not long, just months after the one in Haiti, okay, happened over Christmas. This one's like in January or February. More recently, I think Purdue's had some. Go back here, China. Well, we'll get to that later. Okay, the Ring of Fire. That's where most of the volcanic activity is around those boundaries. Okay, so that's what's happening, converging continental and oceanic plates. But you also have places where oceanic plates converge with those other oceanic plates. And then, who wins, who loses? That's hard to tell. Okay? One of the here is a chain of islands here, and my guess is this may be the edge of the Filipino plate. Remember that plate? Filipino plate went here. That's an oceanic crust. This is oceanic crust in the Pacific. One of them's got to give, but they're both under the ocean. So one subducts under the other, and then you have all this activity going, and there's where the Marianas Islands came from. Look at that, a string of islands right along the boundary of the plate. You have some others down here, the Carolina Islands, but anywhere you see these strings of islands, you can almost bet if it's not a plate boundary, it's a weakness in the plate, a rift in the plate. Well, the Marianas plates, I don't know which is going under which, but one of them is subducting under the other. The trench that's formed there is called the Marianas Trench. That is the deepest point in the ocean, anywhere on the globe. Marianas Trench. We'll see that in a later chapter. So that's when oceanic plate converges with another. One has to subduct under the other. What happens when you have two continental plates converging? That does happen, team. Let's go back and see. Here we go. Here is the India-Australian plate converging with the Eurasian plate. Does anyone know what's up in here? North of India. What's a mountain? Yes! What mountains? The Himalayas. What's special about the Himalayas? The tallest mountains in the world. In fact, I think the 5 or 6 tallest peaks in the world are all right next to each other in the Himalayas. They are big. Mount Everest being the tallest, of course, but others right nearby really forbidding. Why? Because you have two continental plates colliding. Where can they go? They're not subducting under each other, they're colliding this way. The Himalayas are actually growing. The Appalachians are shrinking, okay? The Himalayas and the Rockies too are growing because of pressures that way. So that's what happens with continental plate convergence, okay? Converging continental plates, they got to go up. There's nowhere else to go, okay? So let's look at those three convergences again. Ocean, continental, I forgot they had these, I thought, where are the pictures, okay? The oceanic plate of the denser basaltic material subducted under the less dense granite type continental shelf, and you have the oceanic plate, basalts going down underneath. There's your trench, okay, just outside the boundary. You have this really deep trench, and then it comes back up. So really deepest part is sometimes right near the boundary. So here's your continental plate here being forced upward. Well, what happens? A lot of friction going on here. The oceanic plate is grinding against. I mean, this is not a smooth transition either between the oceanic plate and continental plate, oceanic crust and continental crust, or between the oceanic crust and the mantle that you're getting into here. And you're rubbing in friction, and that's creating a lot of heat, melting a lot of rock, and then typically, if this is also perturbing and breaking that crust a little bit, finds ways to come up, there's volcanoes. Okay? Now we'll see in the map thing in the book, but I'll point out to you here. There's a whole string of volcanic mountains up here. I just was hearing someone recently talk about Crater Lake in Oregon, Mount Shasta, and Mount Rainier is in Washington. Mount Shasta, I think, is in Northern California. Mount Hood, I believe, is all those are volcanoes, okay, that are happening along there. Between spring and summer term, we got to go to Italy, my wife and I, and we took a nephew with us, and a niece flew down from Scotland and joined us. And we went to Pompeii. Pompeii is where two plates are colliding. Mount Vesuvius erupted, buried the city of Pompeii. Only later they discovered it again. Okay, so but that's right down here, southern part of Italy. And by the way, what's just in the northern part of Italy and southern part of France, Germany, another mountain range. Come on, the Alps. And those are where two continental plates are converging. They're growing. Okay, so there's growth in two ways. One way, volcanic activity, one way, uplift. This is more, some uplift, but more volcanic activity is growing that system of coastal mountains because of volcanic, but it could also be because of compression, the oceanic crust pushing up on the continental crust. Okay, so marked by oceanic trench, deep-seated earthquakes, and volcanic mountains inland. Well inland sometimes, but this is where your earthquakes occur too, anywhere along here, because these rocks can easily get hung up and then suddenly let go, and there you have an earthquake. Okay, examples: the convergence of the South American plate and the Nazca plate. Remember that back on this figure. There's a South American plate, Nazca plate being subducted under that, and that's why the Andes Mountains are so tall, so rugged, volcanic activity, and just all other things. Much taller than the Sierra Nevadas that we have in North America. Okay. I think we hit that one pretty much, right? Beat it to death. Okay. Ocean plate convergence. Here the trench in the underwater ridge is created by subduction. Here's the picture of that. You have an oceanic plate, another oceanic plate, and one of them subducts under. Not an easy thing. You got a trench being formed. The Marianas Trench is a lot like this trench. I just don't know which side you're on. You have shallow earthquakes here, deep-seated earthquakes on further down. Where the friction occurs, you have a lot of magma. Where the motion occurs, it can create weaknesses or cracks in the thing. The magma finds its way up. Some of these are completely underwater volcanoes. Other of them have crusted and are forming volcanic islands. And there's the island arc that follows these ocean-ocean plate convergence. I pointed out several on there. The Marianas, the Japanese islands, they are island arcs formed by either an ocean continental plate or ocean plate. Okay. The trench in the underwater ridge is created by subduction associated with deep-seated volcanoes. Okay. The island arcs are where the melted subducted material actually rises above sea level through the overriding plate. The plate is on top. And all this is happening underwater for the longest time, but finally they break the surface. So, in my mind, New Zealand islands, certainly Japanese islands, many of them are exactly that. Indonesia, you'll see they form these arcs. Aleutians, they form those arcs. Okay, continent plate convergence. Okay, the less dense granite-type materials resist subduction; they don't go under, so the colliding plates pile up, producing a deformed and thicker crust of lighter materials. And the Tibetan Plateau, Himalayan mountains, that's classic. Okay, and again, you have continental part of the lithosphere, continental crust, granite materials, lightweight. They can't subduct, or very hard to subduct, so they rise. And I mentioned the Alps, where the African plate is the Eurasian plate. Goes up. Can't go anywhere else. Okay. There's A little bit different things happening with the Rocky Mountains. That's the highest part in North America. That's well inland, but it's still, the pressures from elsewhere are pushing them up. Okay, so it's not actually plate convergence, but still the pressures are pushing up. All right, and then we have the transform boundaries. Okay. By the way, we're now on page. By the way, there's another example here. It's on the rate at which the Atlantic Ocean was spreading, so I'll let you read that. It's pretty interesting. There's a closer look at the top of page 469 on measuring the plate movements. That's a really interesting article. And then the island arcs are described a little bit more than what I said on page 469. Some more examples. Subduction zones, average slope. Again, they sort of made up problems to try to fit them in here. But now transform boundaries on page 470. Okay. These occur when two plates are not diverging from each other or even converging with each other, but they're moving in different directions. Okay? Transform means trans is across. So they're moving crossways from each other. Transform boundaries occur when two plates, and I don't like the verb slide there. Slide makes it sound like it's slippery. It's not slippery, okay? It is definitely rugged, okay? When two plates grind past each other is what I would say. The crust is neither created nor destroyed, as it is with the other type of boundaries, but you have irregularities in movement along the boundaries. And why do you have them? Because they're grinding past each other. Say there's a rock here that juts out into this one trying to move this way, that one trying to move this way. They get hung up, and you don't have motion, but you got the pressure of the motion, and more, and finally something gives, and you have a major earthquake. That's what happens in San Francisco at the turn of the 20th century. That's what happened again, what was it, the 70s or 80s when they had another major earthquake there. It happened down in Los Angeles a few years after that. The crust, the irregularities of movement along the boundary, the sudden jerks, and these are not the politicians, I'm sorry, no, I didn't say that. The sudden jerks produce the earthquakes, when they do get held up. And one of the best examples is the San Andreas fault along the California coastline. And who was it? Was it you, Kayla, that was asking if California's going to fall into the ocean? No, it wasn't. Huh?
It wasn't me.
It wasn't. Somebody asked that right at the end of class, I think last time. Was it you? Yeah. Oh, okay. No, that's not going to happen. That's a transform boundary. There's nothing falling or anything else. Oh, and by the way, earthquakes, we'll talk about this in a later chapter. It's not when the earth opens up and people fall in, cars fall in. That's Hollywood. That's not real, okay? These are just this kind of stuff, sudden motions, okay? One of the prime examples of a transform boundary, the San Andreas fault. Okay. Now, present day I almost missed that. I said present day misunderstandings. There's mistakes and misunderstandings on the same page, but present day understandings are right here. Major question, why do they move? Okay? What drives the plates? Why do they move anyway? Wouldn't they be happy just sitting there? Okay? There's several current working hypotheses, more than one. One is that there's convective cells in the asthenosphere. In other words, remember back here when they showed this? Right there? A place where heat is coming up. Convection is when heat rises, and the convective cells here, that would be kind of forcing their way up. So that's one hypothesis, okay? Convective cells in the asthenosphere. Okay? Hot fluid materials rise at the diverging boundaries. Some escapes to form new crust. The remainder spreads out beneath the lithosphere, dragging the plates further apart, which then opens it up and more comes out. That's one. Okay? Problem with it? We haven't been around a few million years to measure it. Okay? There's not enough data to support the theory. So these aren't even theories yet. These are hypotheses. Yes?
So like right now, going on in Kenya actually split up, so they think that it's breaking out to a whole new continent.
Okay.
So does that represent the same reason why Kenya is actually breaking out from Africa and he's splitting up to his own continent? So is that
What is
Kenya, part of Africa?
Okay.
Is that one of the reasons why?
Okay. That is a diverging boundary. And it's, what is the rift called? It is one that's south of the Red Sea. And yeah, that is the Horn of Africa. It is spreading. It's one of the reasons the Dead Sea is so deep now, because it's spreading. It's falling down into, that's one place it almost is, but not quite. And yeah, Africa, Ethiopia, Egypt, right in there, that east part of Africa, that is one of the places where you have diverging boundary of continental plates. Usually we think of that as in the ocean, but that's actually occurring there. And that is it's a fascinating thing to study and watch. It really is. That might be a great paper topic if that's where you're interested in. Yeah, but this, we don't know why some of this is happening. Okay? Now, this is a very busy slide. They're showing the core way down here. That's where a lot of the heat is coming from. And here's your rift in the crust up there. And this convective motion is doing this kind of stuff and pulling up. Some of this magma makes its way out. Some of it drags the others away. And that's what this is showing here. A hot mantle rock, that which is liquid, the magma, actually comes up, and some of it escapes and makes new surface material. Others drag it out this way. Okay? Now, other things are going on here. Some people claim the weight of this subducted, and this is really drawn wrong here, the weight of this is pulling it apart. Okay? Others saying the magma is pushing it apart. The odds are it's some of both. I don't think it's any one or the other. Okay? So this shows several of the things. This is subduction of the oceanic plate. Beneath this is where they spread apart. This is where they grind together. So this forms earthquakes here, shallow, deep earthquakes. Somewhere down here, there's enough friction that you form magma again, and then that makes its way, especially if all this activity here has made a weaker point in the crust, and then you have volcanic mountains, sometimes way inland, but because it's coming way deep from here. Out in the middle of the ocean, a oceanic plate will subduct beneath another oceanic plate, again because of the rift that's happening here, and that then creates earthquakes along here and volcanic activity here, forming another spring apart islands here. And that's why you form them in arcs like that, because they're along those oceanic trenches. You have these continental to oceanic trenches and ocean to oceanic trenches. These are usually obviously quite big people. Okay? That's the general thoughts. And that's the chapter. The myths, mistakes, and misunderstanding for Lawrence particularly. Bye-bye, California? No. Okay, that was just the theory. In fact, I think Barry Goldwater said it wouldn't be a bad idea. Okay, no, we didn't say that. It's almost time. Person behind the science, Harry Hammond Hess, a good alliterative name. World War II type time frame. He studied much about the Atlantic Ocean, took soundings, readings. He's largely responsible for collecting much of the data that supports the whole theory of plate tectonics today. Good naval officer. Okay, geothermal energy, I talked about that in Iceland. They have it in the Pacific Northwest. Great little blurb to read there. You may find some potential paper topics there. Okay, the book shows a couple of the other illustrations, a little different from the ones on the slide set. But actually, GPS has actually measured plate movement. Because GPS, those are satellites up there, they have measured movement of the plate. Very small, very, very small. In fact, we don't get the most precise GPS. The military gets that. I've heard that they can come close to reading license plates from outer space. We can't, but they can get some very, very precise. Okay, new earthquakes and volcanoes, a little blurb on that. Nothing replaces reading the chapter. So please go back and read the chapter. We've only hit high points here, fill in the gaps. This is a fairly short summary here, so don't count on it giving you everything you need to know. Key terms are sort of a short list here, but they're alphabetical, but they give the page numbers. Applying the concepts, actually a few more than normal. 52 questions here with answers. That's probably the best thing to study for your test. Then you have questions for thought and for further analysis. We'll talk more about those. Yuck. The way we finish the chapter here, the lab we're going to do in this chapter basically only has 10 points worth of materials on it. It's going to be a very short lab on Thursday. So the other 15 points you're going to get from answering any 15 or more of these 20 questions. 16 questions for thought, 4 for further analysis. Total of 20 questions. Part of your lab is going to be to answer any 15 or more of these. Now, why do I say or more? 2 reasons. Great thing to study for the test, okay? But number 2, what if you miss 1 or 2 of them? Well, if you've done a few extra questions, I count up to 15 correct answers. If I get 15 correct answers, you got 10 correct from the lab or something like that, you can still get 25 points even by missing a question or 2. So that's why I say do 15 or more, to guarantee you get as close to 25 points as possible. Now, the reason I'm telling you this now, this is a good study guide for the test. So if you get them done before we do the lab on Thursday, then the test is going to be the last 30 minutes on Thursday. So we'll have a 2-hour lab, and you have time to work on the questions then, so you can wait till then if you want to, and then the 2-hour test, half-hour test. So we'll start Thursday in chapter 19, which is building the Earth's surface. We've already been talking about parts of that, and then we'll do that. Only be an hour and 30 minutes then 2 hours of lab, then 30 minutes of test. So we have a test today and a test on Thursday. These are coming fast and furious now, folks. All right. So, perfect attendance today. Way to go. Ready for your test? I'm going to